In the ceaseless hum of our modern world, beneath the sleek surfaces of technology, lies an invisible pulse, a foundational force that reshaped civilizations. This force, steam, is often relegated to history books, its raw power taken for granted. Yet, its story is intertwined with humanity's relentless quest for energy, a quest that ignited revolutions, forged new landscapes, and continues to drive the engines of our global society. We begin by probing the origins of this potent phenomenon, from theoretical curiosity to practical application, understanding its profound impact. Records suggest that humanity's fascination with steam began centuries before industrialization. In the 1st century AD, the Greek mathematician and engineer Hero of Alexandria documented what is often considered the first steam engine. His aeolipile was a rotating sphere propelled by steam jets. While largely viewed as a novelty or religious mechanism, this device, as described in his manuscript Pneumatica, stands as compelling evidence of an early, albeit theoretical, understanding of steam's mechanical potential. Historians generally agree it was more of a curiosity than a practical tool. For nearly 16 centuries, Hero's concept remained dormant, until a pressing practical problem emerged in Europe: water in mines. As mining operations delved deeper to extract valuable coal and metals, flooding became a critical obstacle. Manual pumping was arduous and inefficient. This dire need for an effective, continuous dewatering solution in the late 17th century provided the impetus for engineers and inventors to revisit the raw power latent within steam, moving from theoretical curiosities to urgent industrial necessities that demanded mechanical innovation. In 1698, English inventor Thomas Savery patented what he called the miner's friend, a steam engine designed specifically for pumping water out of mines. This device operated by creating a vacuum through condensing steam, drawing water upwards, and then using steam pressure to expel it. While rudimentary, often unreliable, and prone to dangerous boiler explosions due to high pressures, Savery's engine marked a significant milestone. It was the first commercially available steam-powered device, demonstrating steam's potential for industrial application, even with its inherent limitations and dangers. A truly transformative leap occurred in 1712 with Thomas Newcomen's atmospheric engine. Unlike Savery's pressure-driven model, Newcomen's engine utilized atmospheric pressure to push down a piston after steam was condensed, creating a vacuum within the cylinder. This design was safer, more reliable, and capable of pumping water from much greater depths. Historical records, such as those kept by early mining companies, indicate its widespread adoption across British and European coalfields, signifying the beginning of steam's practical, sustained role in industry. It dominated for half a century. The Newcomen engine, while revolutionary, was prodigiously inefficient in its fuel consumption. It required vast quantities of coal to boil the water and generate steam. This led to an interesting symbiosis. The engines were most economically viable when located directly at coal mines, where fuel was abundant and cheap. Evidence from mining records of the era shows engine houses often built adjacent to mine shafts, consuming the very resource they helped extract. This relationship cemented coal as the primary energy source for the burgeoning industrial age, linking its extraction to steam's development. The next pivotal figure was James Watt, a Scottish instrument maker. While repairing a Newcomen engine model in 1764, Watt observed its massive energy waste due to repeatedly heating and cooling the cylinder. His crucial insight, patented in 1769, was the separate condenser. By moving the condensing process to a separate chamber, the main cylinder could remain hot, dramatically reducing fuel consumption and increasing efficiency. This innovation, according to engineering historians, transformed the steam engine from an expensive, localized tool into a versatile, economical power source. Watt's partnership with industrialist Matthew Boulton in 1775, forming Boulton and Watt, was instrumental in commercializing his improved engine. Their extended patent, granted by Parliament until 1800, gave them a virtual monopoly over steam engine design. While some historians argue this monopoly stifled competition and delayed further innovations in high-pressure steam, others contend it provided the necessary stability and capital for the engine's widespread adoption and refinement. The rigorous testing and quality control implemented by Bolton and Watt, as documented in their factory records, set new standards for industrial production. Beyond pumping water, Watt's next major innovation was adapting the steam engine to produce rotary motion in the early 1780s. This was achieved through mechanisms like the sun and planet gear, bypassing others' patents. This development was crucial because it allowed steam power to be directly applied to drive factory machinery, such as spinning jennies and power looms. As documented in industrial archives from Lancashire and Yorkshire, the shift from reciprocating pumps to continuous rotary power marked the true unleashing of steam's potential, moving it from mines to manufacturing and catalyzing the factory system. The textile industry, particularly cotton manufacturing, was among the first and most dramatically transformed by steam power. Before steam, production was decentralized, relying on water wheels or manual labor. With steam, factories could be built anywhere, not just beside rivers. Reports from industrial commissions in the late 18th century detail the exponential increase in production capacity. One documented account suggests a single power loom could do the work of several hand weavers. This mechanization drove down costs, increased output, and fundamentally reshaped the British economy, making textiles a global commodity. As factories proliferated, they drew vast populations from rural agricultural areas into burgeoning industrial towns and cities. This rapid urbanization is evidenced by census data from the late 18th and early 19th centuries, showing explosive growth in places like Manchester, Birmingham, and Liverpool. While offering the promise of employment, this mass migration also led to unprecedented social challenges: overcrowded housing, inadequate sanitation, and intense competition for work. The transformation of human settlement patterns, driven by steam-powered industry, fundamentally altered the demographic landscape of nations. The relationship between steam power and metallurgy was symbiotic. Steam engines, especially for pumping air into blast furnaces, allowed for unprecedented scales of iron and later steel production. Conversely, the construction of larger, more powerful steam engines and industrial machinery demanded stronger, more precisely engineered metal components. The availability of high-quality iron, as documented in early industrial ledgers, enabled the construction of more robust machines and the infrastructure to support them. This interplay accelerated innovation in both fields, creating a positive feedback loop of progress. Perhaps no application of steam power captured the public imagination and transformed societies quite like the steam locomotive. Initially used for hauling coal from mines to canals, engineers like Richard Trevithick and George Stephenson soon adapted these engines for passenger and freight transport. The evidence, from early railway company records, clearly demonstrates how railways drastically reduced travel times and freight costs, enabling the rapid distribution of goods and people across vast distances. This network, spreading across continents, forged new economic arteries and reshaped national identities. In 1829, a pivotal moment in railway history occurred: the Rainhill Trials. These were competitive tests to find the best locomotive for the Liverpool and Manchester Railway. George Stephenson's rocket, built with his son Robert, triumphed decisively. The rocket achieved speeds previously unimaginable, reportedly reaching nearly 30 miles per hour, as detailed in contemporary newspaper accounts. This event solidified the steam locomotive's viability and ushered in the age of widespread railway construction, making rocket an enduring symbol of steam-powered speed and industrial progress. Simultaneously, steam technology revolutionized maritime travel. While early steamships, like Robert Fulton's Clermont in 1807, primarily operated on rivers and coasts, continuous improvements in engine design and hull construction soon made ocean voyages feasible. Shipping logs and historical manifests from the mid-19th century demonstrate how steamships drastically reduced transit times and made schedules far more reliable, compared to sail. This fundamentally altered global trade routes, facilitated mass migration, and enabled greater naval projection, shrinking the world and binding distant continents together. A landmark achievement in steam navigation was the voyage of the SS Great Western in 1838. Designed by Isambard Kingdom Brunel, this paddle steamer was the first purpose-built transatlantic liner, making its maiden voyage from Bristol to New York in just 15 days. Contemporary reports, often filled with skepticism before the journey, celebrated its success as a testament to steam's capability. This voyage, alongside the SS Sirius's slightly earlier but less efficient crossing, proved that steam alone could power sustained oceanic travel, forever changing the nature of international communication and commerce. The pervasive nature of steam power visibly transformed the landscape. Rivers once dotted with watermills now saw towering factory chimneys belching smoke. Towns grew around railway lines and engine houses, creating a distinctive industrial aesthetic. Artists like J.M.W. Turner captured this shift, depicting the sublime power of trains and the dramatic skies over coal-fired factories. This reordering of the physical world, evident in countless historical photographs and urban plans, marked a profound departure from agrarian societies, etching steam's indelible mark onto the very geography of nations. While steam brought immense progress, it also ushered in a period of intense human cost. Factory records and parliamentary reports from the 19th century document grueling labor conditions, 12 to 16-hour workdays, 6 days a week, for meager wages. Children as young as 5 were employed in dangerous tasks, often operating fast-moving machinery without adequate safety measures. Accidents, maiming, and death were tragically common. This evidence points to a stark paradox: the power that liberated industry often entrapped individual workers in cycles of poverty and perilous toil, igniting early labor movements. The concentration of steam-powered factories and the rapid growth of urban centers led to unprecedented environmental and public health crises. The burning of vast quantities of coal blanketed cities in smog, contributing to respiratory diseases. Industrial waste polluted rivers, contaminating drinking water and spreading cholera and typhus. Reports from medical professionals and public health officials of the time, such as Edwin Chadwick, vividly describe the squalor and disease prevalent in industrial slums. This evidence directly links the rise of steam-powered industry to severe environmental degradation and a dramatic decline in urban quality of life. The profound economic and environmental transformations wrought by steam power inevitably sparked significant social and political upheaval. The emergence of a powerful industrial capitalist class, alongside a rapidly growing, often exploited, working class, created new tensions. Philosophers and economists like Karl Marx and Friedrich Engels critically analyzed these shifts, as detailed in their seminal works. This era saw the rise of trade unions, reform movements, and new ideologies grappling with the inequalities of industrial society. Evidence indicates that steam, while a force of production, was also an engine of social change and political unrest. Engineers continually sought to increase the power and efficiency of steam engines, often by operating at higher steam pressures. While this yielded greater output, it also introduced significant engineering challenges and dangers. Boiler explosions, often catastrophic, were a constant threat in early high-pressure engines, as detailed in numerous accident reports and coroners' inquests of the era. The scientific understanding of material strength and thermodynamics evolved in parallel with these practical demands, leading to advancements in boiler design, safety valves, and pressure gauges, ultimately making these powerful machines safer. The demands of steam-powered manufacturing also accelerated the development of interchangeable parts and standardized production processes. As factories grew, the need for uniform components that could be easily replaced or assembled became paramount. Evidence from munitions factories and later, sewing machine production, shows a clear shift towards precision engineering and standardized measurements. This manufacturing philosophy, pioneered in part by inventors like Eli Whitney for muskets, was amplified by steam-driven machinery, paving the way for mass production and complex assembly lines in the centuries to come, laying a core principle of modern industry. Steam power also played a crucial role in global geopolitics and imperial expansion. Steamships, unreliant on wind, could navigate rivers and oceans against currents, projecting power and commerce into previously inaccessible territories. Steam-powered railways facilitated the rapid movement of troops, resources, and goods within vast colonial empires, as evidenced by railway construction projects in British India or across Africa. This technological advantage, historians argue, was a key factor enabling European powers to consolidate and maintain their global dominance throughout the 19th century, profoundly shaping the modern world map. The late 19th and early 20th centuries represented the zenith of steam power. Gigantic steam locomotives thundered across continents, luxurious ocean liners traversed the globe, and factories hummed with steam-driven machinery. This was the golden age of steam, where its application permeated almost every aspect of industrial and public life. Photographic archives and industrial records from this period showcase the incredible scale and diversity of steam-powered technology, from mighty battleships to local threshing machines, demonstrating its undisputed dominance as the world's primary mover of mechanical energy. However, new contenders for global energy dominance were emerging. The late 19th century saw rapid advancements in electricity generation and distribution. While early power plants often used steam turbines, electricity itself offered unparalleled flexibility and efficiency in transmitting power over distances. Factories could replace cumbersome belts and shafts with individual electric motors. Historians of technology point to the 1880s and 1890s as the period when electricity began its steady ascent, gradually displacing steam as the preferred direct power source for many industrial and domestic applications. Simultaneously, another revolutionary power source was developing: the internal combustion engine. Fueled by gasoline or diesel, these engines offered high power-to-weight ratios and did not require bulky boilers or water supplies, making them ideal for mobile applications. The invention of the automobile by Carl Benz in 1886 and Rudolf Diesel's engine in 1892 marked the beginning of a profound shift in transportation. While steam still reigned supreme on rails and seas for decades, these new engines presented a compelling alternative, signaling the eventual decline of direct steam power in many sectors. The transition from steam to diesel locomotives on railways exemplifies this gradual displacement. While steam locomotives offered immense power, they were labor-intensive to operate and maintain, requiring frequent water and fuel stops. Diesel-electric locomotives, introduced more widely in the mid-20th century, provided greater efficiency, lower operating costs, and less environmental impact at the point of use. Railway company reports from the 1950s and 60s consistently show the economic advantages of diesel, leading to a widespread dieselization process across railway networks globally, consigning steam to a niche role. By the latter half of the 20th century, the direct applications of steam power receded from everyday life for most people. The factory whistle, once the ubiquitous sound of industry, was replaced by the hum of electric motors. The grand steamships gave way to diesel-powered vessels and jet aircraft. Reports from industrial towns noted the gradual closure of coal mines and steam-powered factories. While steam technology itself didn't vanish, its visible, direct role in driving transportation and smaller-scale industry diminished significantly, becoming less a part of public consciousness. Despite its direct decline, the legacy of steam power is indelibly etched into our physical world. The vast railway networks that span continents, the deep-water ports, and the very urban layouts of our industrial cities are monuments to the steam age. Countless bridges, tunnels, and factory buildings, still in use today, were constructed or enabled by steam technology. Urban planning documents and infrastructure maps reveal how steam's demands for fuel, transport, and manufacturing shape the geography and infrastructure that continues to serve as the backbone of modern society. Crucially, steam did not disappear, it evolved. Today, steam remains the indispensable workhorse for generating approximately 85% of the world's electricity. Modern power plants, whether coal-fired, natural gas, nuclear, or concentrated solar, all fundamentally rely on steam turbines. Fuel is burned or fissioned to boil water, producing high-pressure steam that spins massive turbines, which then drive generators. This indirect application, far removed from visible smokestacks, is a testament to steam's enduring efficiency and power at a colossal scale, silently powering our electric world. Beyond fossil fuels and nuclear reactions, humanity also harnesses naturally occurring steam from the Earth's crust for electricity generation. Geothermal power plants tap into subterranean reservoirs of hot water and steam, directing it to drive turbines. Countries like Iceland, New Zealand, and the Philippines, as documented by geological surveys and energy reports, significantly rely on this renewable steam source. This natural phenomenon, millions of years in the making, highlight steam's fundamental role in planetary processes and our ingenuity in utilizing it for sustainable energy production. Nuclear power, a cornerstone of global energy supply, is fundamentally a steam technology. Nuclear fission reactors generate immense heat, which is then used to boil water, creating high-pressure steam. This steam, in turn, drives turbines to produce electricity. The process is rigorously controlled and contained, ensuring safety while generating vast amounts of power without direct carbon emissions. As reported by the World Nuclear Association, nuclear power plants contribute a substantial portion of emission-free electricity, underscoring steam's crucial, albeit indirect, role in our clean energy future. Far from being a relic, steam technology continues to evolve. Engineers and researchers are developing supercritical and ultrasupercritical steam cycles, where water is heated and pressurized beyond its critical point, significantly increasing efficiency in thermal power plants. Innovations in combined cycle plants, integrating gas and steam turbines, further optimize energy conversion. Ongoing research into carbon capture and storage technologies also seeks to mitigate the environmental impact of fossil fuel-based steam generation. This pursuit of efficiency and sustainability ensures steam will remain a vital component of future energy solutions. While steam's direct industrial role has diminished, its cultural significance endures. Across the globe, heritage railways and museums actively preserve and operate steam locomotives and engines. These efforts, supported by enthusiasts and volunteers, are not merely nostalgic. They serve as living classrooms, offering tangible connections to a pivotal era of human history. Documented heritage events draw millions, providing powerful educational experiences and reminding us of the ingenuity that literally powered the world into modernity, keeping the memory and the physical presence of steam alive for future generations. The story of steam is, at its core, a story of human ingenuity, resilience, and adaptation. From Hero's theoretical Eolipile to Watt's efficient engine and the modern steam turbine, humanity has continuously pushed the boundaries of what's possible with this simple yet profound force. It illustrates our capacity to identify problems, devise solutions, and, crucially, to adapt to the profound societal and environmental consequences of our own inventions. This narrative of challenges met and overcome, or sometimes created, defines much of the human journey through technological progress. The journey of steam from early curiosity to global power source exemplifies the cyclical nature of innovation. An initial discovery, a practical need, a series of incremental improvements, then a revolutionary leap, followed by widespread adoption, eventual displacement by new technologies, and finally, integration into a new, often unseen, role. This pattern, consistently observed across technological history, suggests that even as new energy sources emerge, the foundational lessons learned from steam about power, efficiency, and impact remain profoundly relevant to our ongoing quest for progress. In examining the profound influence of steam, our approach has been to lead with evidence. Historical records, engineering schematics, industrial reports, and academic analyses form the bedrock of our understanding. For example, claims regarding Watt's condenser efficiency are supported by contemporary fuel consumption data from Boulton and Watt. Similarly, the impact of railways is directly verifiable through economic statistics and travel times documented in 19th century ledgers. This rigorous attribution ensures that our narrative is not editorialized opinion, but a factual account derived from the historical record, allowing conclusions to follow naturally. It is also important to acknowledge that historical narratives, particularly regarding invention and priority, are not always monolithic. For instance, while James Watt is credited with the separate condenser, earlier, less successful attempts at similar concepts are sometimes debated among historians. Similarly, the exact contributions of various engineers to the development of the locomotive can vary in different accounts. Our aim is to present the consensus view where it exists, and to note areas where sources or interpretations may differ, ensuring a comprehensive and unbiased understanding of this complex history. Ultimately, the steam engine, in its various manifestations, laid the foundational groundwork for virtually all subsequent industrial and technological advancement. It mechanized production, enabled mass transportation, and spurred the creation of vast energy infrastructures. Without the fundamental lessons learned from harnessing and controlling steam, the development of electricity, internal combustion, and even modern computing systems would have taken vastly different, perhaps slower, paths. Its legacy is not just in what it was, but in what it allowed everything else to become, making it truly a cornerstone of modernity. The influence of steam power runs far deeper than just visible machines and infrastructure. It profoundly reshaped societal structures, economic systems, and even our understanding of time and distance. The fixed schedules of trains and factory shifts imposed new rhythms on daily life. The ability to move goods and people rapidly fostered global markets and interconnected economies. This unseen influence, subtly but powerfully altering the fabric of human existence, is often its most pervasive and lasting impact, demonstrating how a single technological innovation can ripple through every aspect of civilization. The story of steam is but one chapter in humanity's ceaseless quest to understand, control, and harness energy. From fire and muscle to water and wind, and then to steam, electricity, and beyond, each step represents an escalation in our power and our capacity to shape the world. As we face new challenges of climate change and sustainable development, the lessons from the steam age, both its triumphs and its pitfalls, offer invaluable insights into the complex relationship between technological progress and human flourishing. It's an ongoing narrative, written in the very fabric of our civilization. Our present-day world, with its interconnected cities, rapid transit, and pervasive electricity, echoes the steam revolution at every turn. The principles of mass production, the concepts of industrial scale, and the very infrastructure that underpins our global society were either directly created by or profoundly influenced by steam power. Its legacy is not merely historical, it is a living, breathing testament to the power of human ingenuity. Look closely, and you will find its ghost in the machine, its rhythm in the pulse of our modern existence, a constant reminder of where we came from. From a spinning sphere in ancient Alexandria to the colossal turbines generating our electricity today, steam has consistently been a transformative force. It is a story of human ambition, scientific discovery, and profound societal shifts. Though often unseen, its pulse continues to beat at the heart of our energy systems, a fundamental element harnessed across millennia. The tale of steam and humanity is a powerful reminder of how elemental forces, once understood and controlled, can forever alter the course of our civilization, driving us forward with an invisible, yet undeniable, power.